So right now, right this very second, you're lying there beneath roughly 10 trillion tons of air. That's not a metaphor. That's not an exaggeration for effect. The atmosphere sitting on top of you, pressing down on every square inch of your body, stretching all the way up to the edge of space. It genuinely weighs something in the neighborhood of 5 quadrillion kilograms, 5 times 10 to the 18th. And yet you don't feel crushed. You feel comfortable, maybe a little sleepy, which is kind of remarkable when you think about it, because you're living at the bottom of an ocean. Not an ocean of water, but an ocean of gas, and you've spent every single moment of your life submerged in it, and it's so familiar, so constant, so perfectly transparent that most of the time you forget it's even there. But it is there, and it's doing so many things right now, quietly, invisibly, all at once, that if you started listing them, you'd run out of night before you ran out of list. It's keeping you warm. It's filtering out radiation that would otherwise sterilize the surface of the earth. It's carrying water from the oceans to the mountains and dropping it as rain. It's transmitting sound so you can hear my voice, or the hum of whatever's in the room with you. It's scattering sunlight in a way that makes the sky blue during the day and lets it go dark at night. And it's pressing on you right now with a force of about 14.7 pounds per square inch, which is roughly the weight of a bowling ball balanced on every little patch of your skin, and you don't even notice. Here's the thing. For most of human history, nobody understood any of that. The air was just there. It was nothing. Literally nothing. The ancient Greeks had a word for it. They called it keinon, the void. Most early thinkers didn't even consider air to be a substance. It was the absence of substance. You could see through it. You could move through it. It didn't seem to weigh anything or do anything. And if you told Aristotle that the air above his head weighed millions of tons and was pressing on him from every direction, he probably would have laughed, or maybe not laughed. Aristotle wasn't really the laughing type, but he would have dismissed it. Because how could nothing weigh something? And yet Aristotle, for all his blind spots, was actually one of the first people to take air seriously as a physical thing. Around 350 BC, he wrote that air was one of the 4 fundamental elements: earth, water, air, and fire. And he argued that air had real physical properties. He noticed, for example, that a leather bag full of air weighed more than an empty one, which seems obvious to us now, but think about what that meant in the 4th century BC. It meant air had weight. It meant the invisible stuff all around you was made of something. That was a genuinely radical observation, and Aristotle deserves credit for it, even though he got an enormous amount wrong about how the atmosphere actually behaved. But here's what's fascinating. After Aristotle, that insight basically went nowhere for almost 2,000 years. 2,000 years. The idea that air had weight and could exert pressure just sat there, gathering dust in old manuscripts, while generation after generation of scholars argued about philosophy and theology and the nature of the heavens without ever really testing any of it. And the reason it went nowhere is actually kind of important for understanding how we eventually figured out the atmosphere. Nobody had the tools. You can't study air pressure if you don't have a way to measure it. You can't understand the atmosphere if you can't get above it, or weigh it, or trap it, or watch what happens when you remove it. The atmosphere is, in a very real sense, the hardest thing in the world to study, because you're inside it. Always. You can't step outside the atmosphere and look at it from a distance the way you can look at a mountain or a river. You're a fish trying to understand water. So the story of how we figured out the atmosphere is really a story about instruments. about clever people building devices that let them see the invisible. And that story really starts, in the early 1600s, in Italy, with a problem that had nothing to do with science at all. It had to do with pumps. Here's the setup. In the late 1500s and early 1600s, miners and engineers across Europe were using suction pumps to pull water out of mines and wells, and these pumps worked fine for shallow wells. You'd create a vacuum at the top of a pipe, and the water would rise up to fill it. Simple, except that the water would never rise more than about 32 or 33 feet. No matter how good your pump was, no matter how perfect your seal, the water just stopped rising at around 10 meters. And nobody could explain why. Now, the standard explanation at the time was based on Aristotle's old idea that nature abhors a vacuum. Horror vacui. The idea was that the universe simply couldn't tolerate empty space, so when you created a vacuum at the top of a pipe, nature would rush to fill it, pushing water upward. But if nature truly abhorred a vacuum, why did it stop abhorring it at 33 feet? Did nature only sort of abhor a vacuum? Did it abhor it up to a point and then shrug and give up? That didn't make any sense, and the contradiction bothered a lot of people, but nobody had a better explanation. Enter Galileo. Galileo Galilei was aware of this problem. He mentions it in his final major work, The Discourses and Mathematical Demonstrations Relating to Two New Sciences, published in 1638. He didn't solve it, but he framed it in a way that pointed toward the answer. He suggested that the vacuum itself had a kind of limited force, and that the weight of the water column eventually exceeded that force. He was wrong about the mechanism, but he was right that something quantitative was going on, that there was a specific, measurable limit, and that limit had to have a physical explanation. Galileo died in 1642, but his insight passed to one of his students, a brilliant young mathematician named Evangelista Torricelli. And Torricelli had a hunch. What if the water wasn't being pulled up by the vacuum at all? What if it was being pushed up from below, by the weight of the atmosphere pressing down on the surface of the water in the well? If that were true, then the reason the water stopped rising at 33 feet was simply that a column of water 33 feet tall weighed exactly as much as the column of air above it, stretching all the way to the top of the atmosphere. The atmosphere was pushing down, the water was pushing up, and at 33 feet they balanced. This was a completely revolutionary idea. It meant the atmosphere had weight, real, measurable weight. And it meant you could calculate that weight by seeing how high it could push a column of liquid. But here's the clever part. Torricelli realized that if he used mercury instead of water, the column would be much shorter, because mercury is about 13.5 times denser than water. So instead of needing a 33-foot tube, he'd only need one about 30 inches tall. Much more practical for an experiment. So in 1643, Torricelli took a glass tube about 3 feet long, sealed at one end, filled it completely with mercury, put his thumb over the open end, flipped it upside down, and submerged the open end in a dish of mercury. And when he removed his thumb, the mercury in the tube didn't all pour out. It dropped a little, then stopped, settling at a height of about 29.5 inches above the surface of the mercury in the dish. And above the mercury in the tube, in that sealed top portion, there was nothing. A vacuum, the first sustained vacuum ever created by a human being. Think about what that moment meant. Torricelli had just proved two things at once. First, he'd proved that vacuums could exist, that nature did not, in fact, abhor them. And second, he'd proved that the atmosphere had weight, and that its weight was exactly enough to support a column of mercury about 30 inches tall. He had, in effect, built the first barometer. He'd built a device that could weigh the atmosphere. And here's what's really lovely about this. Torricelli understood immediately what his instrument was telling him. He wrote to his friend, Michelangelo Ricci. And yes, this is a different Michelangelo. And in that letter, he said something that I think is one of the most beautiful sentences in the history of science. He said, "We live submerged at the bottom of an ocean of air. Noi viviamo sommersi nel fondo d'un pelago d'aria." That was 1644, and that one sentence basically invented atmospheric science. Because once you understand that you're living at the bottom of an ocean, everything else follows. The pressure you feel is just the weight of all that air above you. The weather is just currents and waves in that ocean. Wind is the air flowing from one place to another, just like currents in the sea. But of course, not everyone believed Torricelli. Plenty of people still clung to the horror vacui idea. And so the next crucial step came from a French polymath named Blaise Pascal. Pascal was only in his 20s at this point. He was one of those terrifyingly precocious geniuses who was publishing original mathematical proofs as a teenager. And when he heard about Torricelli's experiment, he immediately grasped its implications and designed a way to test them. Pascal's reasoning was elegant. If the mercury in the tube was being held up by the weight of the atmosphere, then if you carried the tube to a higher elevation, say up a mountain, there would be less atmosphere above you, so the mercury should drop. If, on the other hand, the mercury was being held up by nature's abhorrence of a vacuum, then the height shouldn't change, because nature presumably abhorred vacuums just as much on a mountaintop as in a valley. The problem was that Pascal was in poor health. He'd been sickly for most of his life, and climbing a mountain was not really in the cards for him. So he wrote to his brother-in-law, Florent Perrier, who lived near the Puy de Dôme, a volcanic peak in central France that rises about 1,000 meters above the surrounding plain, and he asked Perrier to carry a Torricelli tube up the mountain and record the mercury height at different elevations. Perrier did the experiment on September 19th, 1648. He set up one tube at the base of the mountain as a control, with a monk watching it to make sure the mercury level didn't change. Then he carried a second tube up the mountain, stopping at various points to check the mercury height. And the results were exactly what Pascal had predicted. At the base, the mercury stood at about 26 inches and 3.5 lines, the old French measurement system. At the summit, it had dropped by more than 3 inches. 3 inches. That's a huge difference. And the control tube at the bottom hadn't budged. When Pascal received the results, he was thrilled. He published them widely, and the experiment became one of the most famous in the history of physics. It proved beyond any reasonable doubt that atmospheric pressure decreased with altitude, which meant the atmosphere had a finite height and a real, measurable weight that varied depending on how much air was above you. And this is where things start to get really interesting, because once you accept that the atmosphere has weight and that its pressure decreases as you go up, you immediately start asking new questions. How fast does the pressure decrease? Does it decrease steadily, or does it change rate? How high does the atmosphere actually go? What's it made of? Is it the same stuff all the way up, or does it change? And what about all those things the atmosphere does? The wind, the rain, the clouds, the storms. How do those work, mechanically, in terms of pressure and temperature, and the movement of air masses? These are the questions that would occupy some of the sharpest minds in Europe for the next 2 centuries. And the answers, when they came, would turn out to be far stranger and more beautiful than anyone in Torricelli's day could have imagined. Because the atmosphere isn't just a uniform blanket of air sitting on top of the Earth, it's a layered, dynamic, constantly churning system with structure and behavior that emerges from a handful of basic physical principles interacting in ways that are simple to state and astonishingly complex to predict. But before we can talk about that structure, there's one more piece of the foundation we need to lay, and it involves a man who was, in many ways, the opposite of Pascal. Not sickly and introspective, but robust, practical, and spectacularly theatrical. His name was Otto von Guericke, and he was the mayor of Magdeburg, a city in what is now Germany, and in 1654, just 6 years after Perrier climbed the Puy de Dôme, von Guericke staged one of the most dramatic scientific demonstrations in history. He wanted to show, once and for all, just how powerful atmospheric pressure really was. And the way he did it involved 2 bronze hemispheres, a vacuum pump he'd invented himself, and 16 horses. 2 teams of 8, hitched to opposite sides. Von Guericke had these 2 bronze hemispheres, each about the size of a large mixing bowl, maybe 20 inches across, machined so their rims fit snugly together. And then, using an air pump he'd designed and built himself, he evacuated the air from inside, just sucked it out. And once the air was gone, those 2 hemispheres were held together by nothing but the pressure of the atmosphere pushing in on them from every direction. There was no latch, no lock, no glue, just air pressure on the outside and near vacuum on the inside. And then he hitched up the horses, 8 on one side, 8 on the other, pulling in opposite directions, straining against each other, and the hemispheres held. They would not come apart. 16 horses could not overcome the force of the atmosphere pressing those 2 half-shells together. Now think about what that means. Think about the surface area of those hemispheres. The atmosphere was pushing on every square inch of that bronze surface with roughly 15 pounds of force. Add it all up across the whole face of the hemisphere, and you're talking about thousands of pounds of total force holding those 2 pieces together. Von Guericke knew this. He'd calculated it. But calculations on paper are one thing. Watching 2 teams of horses fail to pull apart 2 empty bowls is something else entirely. The crowd reportedly gasped. Some accounts say the hemispheres finally came apart with a loud bang when the seal gave way, and people flinched like a cannon had gone off. And here's what made von Guericke so important to the story of understanding the atmosphere. He wasn't just demonstrating a curiosity. He was making atmospheric pressure visceral, undeniable, something you could see and hear and feel in your gut. Torricelli had proved it with mercury in a tube. Pascal had proved it with measurements on a mountain. But von Guericke proved it with theater, with spectacle. And sometimes that's what it takes to shift how an entire culture thinks about something invisible. After the Magdeburg hemispheres, nobody could seriously argue that air had no weight, no force, no real physical presence. The atmosphere was powerful. It was pressing down on everything, all the time. And now the question became, what exactly is this stuff, and how does it behave? This is where Robert Boyle enters the picture. And honestly, Boyle is one of those figures who deserves more recognition than he gets outside of chemistry classrooms. Born in 1627, he was the 14th child of the Earl of Cork, one of the wealthiest men in Britain. So Boyle had resources, he had education, he had time, and he had an insatiable curiosity about the natural world, particularly about air. Working with his brilliant assistant Robert Hooke, yes, the same Robert Hooke who would later feud bitterly with Isaac Newton, Boyle built an improved version of von Guericke's air pump and started running experiments. Dozens of them. Hundreds, eventually. He put candles inside glass vessels and pumped out the air and watched them go out. He put mice in there. And yes, this is grim by modern standards. And observed that they couldn't survive without air. He put bells inside and showed that sound couldn't travel through a vacuum. Each experiment peeled back another layer of what air actually was and what it did. But the discovery that matters most for understanding the atmosphere, the one that still bears his name, came in 1662. Boyle's Law. And it's beautifully simple. He found that if you take a sealed quantity of air and compress it, push it into a smaller space, its pressure increases in exact proportion. Double the pressure and the volume halves. Triple the pressure and the volume drops to a third. The relationship is precise and mathematical. Pressure times volume equals a constant as long as the temperature stays the same. Now, why does this matter for the atmosphere? Think about it this way. Imagine a column of air stretching from the ground all the way to the top of the atmosphere. The air at the very bottom of that column has the weight of all the air above it, pressing down on it. So it's compressed. It's squeezed into a denser state. The air a few miles up has less air above it, so less weight pressing down. So it's less compressed, less dense. And the air way up high, near the edge of space, has almost nothing above it at all, so it's incredibly thin, barely there. Boyle's law gives you the mathematical framework to understand this gradient. It tells you that the atmosphere isn't just getting thinner as you go up, it's getting thinner in a specific, predictable, exponential way. The pressure doesn't drop by the same amount for each mile you climb. It drops by the same fraction. Roughly speaking, for every 18,000 feet or so you ascend, about 3.5 miles, the pressure halves. So at sea level, you've got the full 15 pounds per square inch. At 18,000 feet, about 7.5. At 36,000 feet, about 3.75. And so on. This exponential decay is fundamental. It means that the vast majority of the atmosphere's mass is packed into the lowest portion. Something like half of all the air in the atmosphere is below 18,000 feet. 90% of it is below about 50,000 feet, roughly 10 miles up. The atmosphere extends much higher than that, hundreds of miles technically, but it gets so thin so fast that most of what matters, most of what we experience as weather and breathable air, is crammed into this relatively thin shell hugging the surface. And here's something lovely about this. It means the atmosphere, for all its vastness when you look up at the sky, is actually astonishingly thin relative to the size of the Earth. The Earth's diameter is about 8,000 miles. The bulk of the atmosphere, the part that contains almost all the weather and almost all the air, is maybe 10 miles thick. That's a ratio of about 800 to 1. People sometimes use the analogy of an apple. If the Earth were an apple, the atmosphere would be thinner than the skin. And that's not poetic exaggeration. That's roughly accurate. This thin, fragile, gossamer layer is everything. It's all the air we breathe, all the weather we experience, all the protection we have from the radiation of space. Just this whisper-thin shell. So by the late 1600s, thanks to Torricelli, Pascal, von Guericke, Boyle, and Hooke, the basic physical reality of the atmosphere was becoming clear. It's a gas with weight. It exerts pressure. That pressure decreases with altitude in a predictable way. The air is compressible. Squeeze it, and it gets denser. Release it, and it expands. These are the ground rules. But knowing the ground rules and understanding the game are very different things. Because the atmosphere doesn't just sit there. It moves, it churns, it creates wind and storms and calm days and violent hurricanes and gentle breezes and everything in between. And to understand why it moves, you need to understand heat. This is where the story shifts from the physics of pressure to the physics of energy. And the key figure here is a man named Edmund Halley. Yes, that Halley, the one the comet is named after. Halley was a polymath in the truest sense, an astronomer, a mathematician, a navigator, a cartographer, and in 1686 he published a remarkable paper that attempted to explain the global pattern of trade winds, those steady, reliable winds that blow from east to west across the tropics, and that had been carrying sailing ships across oceans for centuries. Sailors knew these winds intimately. They depended on them. But nobody had a convincing explanation for why they blew the way they did. Halley's insight was that the sun is the engine. The sun heats the Earth's surface unevenly, more at the equator, less at the poles. And this uneven heating is what drives the atmosphere to move. Think about it like this. When the sun heats the ground near the equator, that ground heats the air directly above it. Warm air expands. Boyle would have appreciated this. It becomes less dense, and less dense air rises. It has to. It's buoyant, like a bubble in water. So you get this massive upwelling of warm air along the equatorial belt, rising up into the atmosphere. And as that air rises, it leaves a kind of partial void at the surface, a zone of slightly lower pressure. Air from the north and south rushes in to fill that void. That's wind. That's the fundamental mechanism. Uneven heating creates pressure differences, and pressure differences create air movement, and air movement is wind. Halley got the broad strokes right, and that's impressive for 1686. But he got some details wrong. And the reason he got them wrong is fascinating, because it points to a force that would take another century to be properly understood. A force that is absolutely central to how the atmosphere behaves, and that is, frankly, one of the most counterintuitive things in all of physics. It's called the Coriolis effect, and it arises from the simple fact that the Earth is spinning. Here's the thing about the Coriolis effect. It's not really a force in the way gravity is a force. It's more of an apparent force, something that shows up because we're observing motion from a rotating frame of reference. But its consequences are enormous. It's the reason hurricanes spin. It's the reason the trade winds blow from the northeast in the northern hemisphere and from the southeast in the southern hemisphere, rather than blowing straight north to south the way Halley originally proposed. It's the reason weather systems in the mid-latitudes tend to move from west to east. And understanding it requires you to think carefully about what it means to be standing on a planet that's rotating at about 1,000 miles per hour at the equator. Imagine you're standing at the equator. The Earth beneath your feet is moving eastward at roughly 1,000 miles per hour. You don't feel it, of course, because everything around you, the air, the ground, you, is all moving together. Now imagine a parcel of air at the equator that gets heated, rises, and then starts flowing northward toward the pole at high altitude. As it moves north, it's leaving the equator, where the Earth's surface is moving eastward very fast, and heading toward higher latitudes, where the Earth's surface is moving eastward more slowly, because the circle of latitude is smaller, so the surface doesn't have to travel as far to complete one rotation in 24 hours. But that parcel of air still has the eastward momentum it picked up at the equator. So relative to the ground beneath it, as it moves north, it starts drifting east. It curves. From the perspective of someone standing on the ground watching it, the air appears to be deflected to the right. In the southern hemisphere, the same logic applies in mirror image. Air moving away from the equator appears to deflect to the left. This was first described mathematically by Gaspar Gustave de Coriolis in 1835 in a paper that was actually about rotating machinery, not about weather at all. Coriolis was working on the physics of water wheels and rotating systems in factories. But the mathematics he developed turned out to apply perfectly to the largest rotating system any of us will ever stand on, the Earth itself. And when meteorologists finally incorporated the Coriolis effect into their understanding of atmospheric circulation, everything started clicking into place. The trade winds, the westerlies, the polar easterlies, the great rotating storm systems, all of it could be traced back to two fundamental drivers: uneven solar heating and the rotation of the Earth. Heat provides the energy. Rotation provides the twist. And between those two things, you get the entire architecture of global wind patterns. Think of it as a giant heat engine with moving parts, and once you see how those parts fit together, you'll never look at a weather map the same way again. So let's start at the equator, because that's where the story begins. The equator gets more direct sunlight than anywhere else on the planet. The sun is nearly overhead year-round, and all that energy pours into the surface, the ocean, the land, and the surface heats the air above it. That warm air expands, becomes less dense, and rises. We talked about this with Halley's model. But here's what actually happens when that air rises at the equator. It doesn't just go straight to the poles the way Halley imagined. It can't. The Coriolis effect won't let it. That rising equatorial air climbs high into the troposphere. We'll talk more about what the troposphere actually is later, but for now, just think of it as the lowest layer of the atmosphere, the one where all our weather happens, extending roughly 10 to 15 kilometers above the surface. The warm air rises to near the top of this layer, and then it starts spreading outward, heading toward the poles. But as it moves north or south, the Coriolis effect starts curving it. By the time it's traveled about 30 degrees of latitude, roughly the latitude of Cairo or Houston or Shanghai, that air has been deflected so strongly to the east that it's no longer making much progress toward the poles. It's essentially moving sideways. And as it's been traveling, it's been radiating heat away into space, cooling down, becoming denser. So it sinks. It piles up and descends back toward the surface around 30 degrees north and 30 degrees south. This creates a beautiful closed loop. Air rises at the equator, flows poleward at high altitude, sinks around 30 degrees, and then flows back toward the equator along the surface to replace the air that's rising. That surface flow gets deflected by the Coriolis effect too. In the northern hemisphere, it curves to the right, which means the surface winds end up blowing from the northeast. In the southern hemisphere, they curve to the left and blow from the southeast. And those are the trade winds. The same trade winds that carried Columbus across the Atlantic. The same ones that shaped centuries of maritime commerce and colonial history. They're not random. They're not mysterious. They're the surface return flow of a giant convection cell driven by solar heating and shaped by the Earth's rotation. This cell, the one between the equator and about 30 degrees latitude, is called the Hadley cell, named after George Hadley, an English lawyer and amateur meteorologist who proposed this circulation pattern in 1735. Hadley was the first person to realize that the Earth's rotation had to be involved in explaining the trade winds. He didn't have the formal mathematics that Coriolis would develop a century later, but he had the right intuition. He understood that the spinning Earth would deflect the winds, and he built a conceptual model that was remarkably close to what we understand today. For an amateur working in the early 18th century, It was a stunning piece of physical reasoning. Now, here's something lovely about where that sinking air comes down. Around 30 degrees latitude, when air sinks from high altitude, it compresses and warms. Warm, descending air is extremely dry because as air warms, its capacity to hold moisture increases, and so its relative humidity drops. The result is that the regions around 30 degrees north and south are dominated by high pressure and dry, stable conditions. And if you look at a map of the world's great deserts, they line up almost perfectly with these latitudes: the Sahara, the Arabian Desert, the Sonoran Desert in the American Southwest, the Kalahari in southern Africa, the Australian outback. These aren't deserts by coincidence. They're deserts because the atmosphere's circulation is literally wringing the moisture out of the air and delivering dry, sinking air to those latitudes. The geometry of the planet and the physics of its rotation conspire to create bands of aridity. That's remarkable when you think about it. The reason the Sahara exists is fundamentally the same reason the trade winds blow. And it goes further. The band where the trade winds from the northern and southern hemispheres converge, right near the equator, where all that air is rising, is called the Intertropical Convergence Zone, or the ITCZ. Sailors had another name for it, the doldrums, because the dominant motion of air there is vertical, not horizontal. The surface winds near the ITCZ are often light and variable. Sailing ships could get becalmed for days or weeks, drifting in oppressive heat and humidity while the crew went slowly mad. The word doldrums literally came to mean a state of listlessness and stagnation because of what sailors experienced in this zone. Meanwhile, those bands of sinking air around 30 degrees, sailors called them the horse latitudes. The origin of that name is debated. One story, possibly apocryphal, is that ships carrying horses to the New World would sometimes have to throw the animals overboard to conserve water when they were becalmed in these high-pressure zones. Whether or not that's true, the name stuck, and the meteorology behind it is solid. Light winds, clear skies, sinking dry air. Not a great place to be on a sailing ship with no engine. So the Hadley cell handles the tropics. But what about the rest of the atmosphere? The air that sinks at 30 degrees, some of it flows back toward the equator as the trade winds, but some of it flows poleward along the surface. And this creates a second circulation cell. The surface air moving poleward from 30 degrees gets deflected by the Coriolis effect, and in the northern hemisphere, it curves to the right, producing the prevailing westerlies, winds that blow generally from the west toward the east. These are the winds that dominate the weather patterns across most of the United States, across Europe, across the mid-latitudes of both hemispheres. If you've ever noticed that weather systems in the U.S. generally move from west to east, storms forming over the Pacific and tracking across the country, that's the westerlies at work. This mid-latitude cell is called the Ferrel cell, named after William Ferrel, an American meteorologist who described it in the 1850s. Ferrel was a fascinating character, largely self-taught. Born in a log cabin in what is now West Virginia, he worked as a school teacher while doing meteorological research on the side. He was one of the first people to work out a comprehensive mathematical model of atmospheric circulation that incorporated the Coriolis effect properly. His work was published in obscure journals and initially got very little attention, but it turned out to be foundational. The Ferrel cell is actually the most complex of the three major circulation cells because it's not directly driven by heating the way the Hadley cell is. It's more of an indirect cell, driven by the interaction between the Hadley cell to its south and the polar cell to its north. It's like a gear that turns, because the gears on either side of it are turning. The air in the feral cell actually rises at around 60 degrees latitude and sinks at around 30 degrees, which is thermodynamically a bit odd. It's rising in a cooler region and sinking in a warmer one, which is the opposite of what you'd expect from simple convection. It works because it's being mechanically driven by the momentum of the cells flanking it. And then there's the polar cell, the third and final piece. Near the poles, the air is bitterly cold and dense. It sinks over the pole, flows outward along the surface toward lower latitudes, gets deflected by the Coriolis effect, and creates the polar easterlies, surface winds blowing from the east. This cold surface air eventually meets the warmer air flowing poleward from the feral cell, and where they collide, around 60 degrees latitude, you get a zone of rising air and low pressure. This boundary between cold polar air and warmer mid-latitude air is called the polar front, and it's one of the most meteorologically active zones on Earth. The polar front is where a huge fraction of the mid-latitude weather systems are born. The cyclones, the frontal systems, the bands of rain and snow that sweep across the northern United States, across Britain, across northern Europe and Russia. So picture the whole thing. 3 cells in each hemisphere, stacked from equator to pole. The Hadley cell from the equator to about 30 degrees. The feral cell from about 30 to about 60 degrees. The polar cell from about 60 degrees to the pole. Multiply by 2 hemispheres, and you've got 6 great circulation cells girdling the planet with alternating bands of surface winds, easterly trade winds in the tropics, westerlies in the mid-latitudes, polar easterlies near the poles, and alternating zones of rising and sinking air that create bands of wet and dry climates. It's an elegant system, and it emerges from just those 2 ingredients we identified, differential solar heating and planetary rotation. But here's the thing. This 3-cell model is a simplification, a beautiful, useful simplification, but a simplification nonetheless. The real atmosphere is messier, more turbulent, more chaotic. The boundaries between cells shift with the seasons. The ITCZ migrates north and south, following the sun, which is why monsoon climates exist. The seasonal shift of the ITCZ over the Indian subcontinent is what drives the Indian monsoon, one of the most consequential weather phenomena on Earth, affecting the lives and livelihoods of over 1 billion people. The Hadley cells expand and contract. The jet streams, those rivers of fast-moving air high in the atmosphere, meander and buckle in ways that can lock weather patterns in place for weeks. And the jet streams, let's talk about those for a moment, because they're one of the most fascinating features of the atmosphere, and they weren't even discovered until the 20th century. The jet stream is essentially a narrow band of very strong winds. We're talking speeds of 100 to 200 miles per hour or more, that flows roughly from west to east at high altitudes, typically around 30 to 40,000 feet, right near the top of the troposphere. There are actually several jet streams, but the 2 most important ones are the polar jet stream, which sits near the boundary between the feral and polar cells around 60 degrees latitude, and the subtropical jet stream, which sits near the boundary between the Hadley and feral cells around 30 degrees. The existence of these high-altitude wind rivers was suspected by a few researchers in the early 20th century. A Japanese meteorologist named Wasaburo Uishi was doing remarkable work in the 1920s, launching weather balloons from a site near Mount Fuji and tracking their paths. He documented consistently strong westerly winds at high altitudes and published his findings in Esperanto, the constructed international language, which meant almost nobody in the Western meteorological community read them. It's one of those quietly tragic stories in the history of science. A researcher doing groundbreaking work that gets overlooked because of a language barrier. And not even a natural language barrier, but an artificial one. Uishi's observations were essentially rediscovered independently by other researchers, and the jet stream became widely known to Western meteorologists only during World War II, when American bomber crews flying missions over Japan at high altitude encountered unexpectedly fierce headwinds that slowed their ground speed to a crawl. Imagine that. You're a B-29 crew member in late 1944, flying at maybe 28 or 30,000 feet over the Pacific, and you're supposed to be making a bombing run, and your airspeed indicator says you're doing 250 miles an hour, but when you look down at the ground, or when your navigator does the math, you're barely moving forward, maybe 60, 70 miles per hour over the ground. That's slower than a car on a highway, because you're flying straight into a river of air that's blowing against you at nearly 200 miles per hour. Your engines are burning fuel at the normal rate, your instruments say everything is fine, but the atmosphere itself is acting like a conveyor belt running the wrong direction. Crews reported missions where they simply could not reach their targets because the headwinds ate up so much fuel they'd have to turn back. And when they did reach the target, their ground speed was so slow, or so fast on the return trip, that their bombing accuracy was terrible. The bombardier's calculations were all built around certain assumptions about ground speed, and those assumptions just fell apart at altitude over Japan. Now here's what's interesting about this from a purely atmospheric science perspective. Those bomber crews weren't just encountering some random patch of strong wind. They were flying directly through the subtropical jet stream, which flows powerfully from west to east across the Pacific at exactly the altitudes where B-29s operated. And the jet stream over Japan is particularly strong in winter because of the enormous temperature contrast between the frigid Siberian air mass to the north and the warm Pacific air to the south. That temperature gradient is what drives the jet stream's intensity. The bigger the temperature difference between the air masses on either side of the jet, the faster the wind blows. We'll come back to why that is in a moment, because the mechanism behind jet streams is genuinely elegant once you see it. But first, let's stay with the war for a second, because the story takes a turn that connects back to Uishi in a way that's almost poetic. The Japanese military, it turns out, did know about the high-altitude westerlies, in part because of Uishi's earlier work. And in late 1944, they launched a remarkable and frankly kind of desperate weapon system called the Fugo balloon bomb. The idea was to release hydrogen balloons carrying incendiary devices from the Japanese coast, let the jet stream carry them across the Pacific, a journey of roughly 5,000 miles, and have them descend over the forests and cities of North America, starting fires. They launched around 9,000 of these balloon bombs between November 1944 and April 1945. And here's the thing. Some of them actually made it. Around 300 were confirmed to have reached North America, landing in places from Alaska to Mexico, from the Pacific coast all the way to Michigan. One killed 6 people in Oregon, a woman and 5 children on a church outing who found one of the devices in the woods and it detonated. They were the only confirmed casualties from enemy action on the U.S. mainland during the entire war. It's a sobering detail. The military kept the balloon bomb program classified to prevent panic and to deny Japan any feedback about whether the weapons were working, which is partly why this story isn't better known. But think about what the Fugo program represents in terms of atmospheric understanding. The Japanese military was essentially using the jet stream as a delivery system, a natural, invisible highway in the sky that reliably flows from west to east at high altitude. They understood its consistency, its altitude, its speed, well enough to engineer a weapon around it. And on the American side, the encounter with those same winds was a rude surprise that forced a complete rethinking of high-altitude bombing tactics. General Curtis LeMay eventually shifted to low-altitude nighttime incendiary raids over Japan, partly because the high-altitude precision bombing just wasn't working, and the jet stream was one of the major reasons why. So this invisible feature of the atmosphere, this narrow ribbon of screaming wind at 30,000 feet, directly shaped the course of the war in the Pacific. Now, let's talk about why jet streams exist at all, because the mechanism is beautiful, and it ties together everything we've been building up. You've got these large circulation cells, the Hadley cell, the Farrell cell, the polar cell, and at the boundaries between them, you get sharp temperature gradients. On one side of the boundary, air is significantly warmer. On the other side, significantly cooler. Now, remember how we talked about pressure decreasing with altitude? Here's the key insight. Warm air is less dense than cold air, so a column of warm air is taller. It extends higher than a column of cold air, even if the surface pressure is similar. What that means is that at high altitude, the pressure on the warm side is actually higher than the pressure on the cold side, because the warm column still has significant atmosphere above you at a height where the cold column has already thinned out. So you get a pressure gradient at altitude that pushes air from the warm side toward the cold side. But as soon as that air starts moving, the Coriolis effect, remember Coriolis, that deflection from Earth's rotation, bends it to the right in the northern hemisphere, and the air ends up flowing not from warm to cold, but roughly parallel to the temperature boundary, from west to east. And that flow, concentrated into a narrow band by the sharpness of the temperature gradient, is the jet stream. It's essentially the atmosphere's response to a steep temperature cliff. The steeper the cliff, the more dramatic the temperature contrast. The faster the jet stream blows. That's why jet streams are stronger in winter, when the temperature difference between tropical and polar air is at its greatest. And it's why the polar jet stream, which sits along that volatile boundary between cold polar air and milder mid-latitude air, is the one that matters most for day-to-day weather in places like the United States, Europe, and Northern Asia. And here's where it gets really practical, really relevant to your life. The polar jet stream doesn't flow in a straight line. It meanders. It develops these big north-south waves. Meteorologists call them Rossby waves, named after Carl Gustav Rossby, a Swedish-American meteorologist who worked out their dynamics in the late 1930s. Rossby was one of those figures who transformed the field. Born in Stockholm in 1898, he studied under Wilhelm Bjerknes, a name we'll get to shortly, because Bjerknes is arguably the father of modern weather forecasting, and eventually moved to the United States, where he established the meteorology department at MIT, and later at the University of Chicago. Rossby realized that the large-scale flow patterns in the atmosphere behave like waves, and these waves, typically 3 to 6 of them circling the globe at any given time, determine where cold air plunges south and where warm air surges north. When a Rossby wave develops a deep trough, that's a dip in the jet stream where Arctic air spills southward. When it develops a ridge, that's a northward bulge where warm air pushes poleward. And the thing about Rossby waves is that they move. They propagate. Usually they drift slowly eastward, which is why weather systems in the mid-latitudes generally move from west to east. But sometimes, And this is where it gets really consequential. Sometimes these waves stall. They get locked in place. And when that happens, you get what meteorologists call a blocking pattern. A blocking high-pressure system can park itself over a region and just sit there for days or even weeks, deflecting storms around it, trapping the same weather in place. If it's summer, you get a prolonged heat wave. If it's winter, you might get an extended cold snap. Some of the most extreme weather events in recent history: the 2003 European heat wave that killed tens of thousands of people, the 2010 Russian heat wave that devastated crops and caused catastrophic wildfires, have been linked to blocking patterns where the jet stream got stuck. So this feature of the atmosphere that bomber crews stumbled into during World War II, this river of wind at 30,000 feet, turns out to be one of the primary controls on the weather you experience at the surface. When the jet stream is flowing fast and relatively straight, weather systems move through briskly. You get a few days of rain, then it clears, then maybe another system comes through. Normal, changeable weather. But when the jet stream weakens and gets wavier, weather patterns become more persistent and more extreme. And there's growing evidence, still debated, still being studied, but increasingly supported by data, that as the Arctic warms faster than the rest of the planet, the temperature gradient that drives the polar jet stream is weakening, which may be making the jet stream wavier and more prone to these blocking patterns. But that's a thread we'll pick up later. For now, let's come back down from 30,000 feet and think about what's happening in the atmosphere closer to the ground, because all of this large-scale circulation, the cells, the jet streams, the Rossby waves, that's the big picture. That's the general circulation. But the weather you actually feel, the rain on your window, the thunderstorm on a summer afternoon, the fog that rolls in at dawn, that happens at a much smaller scale. And it happens because of something we haven't really explored yet. Water. Water is the wild card in the atmosphere. It's the thing that makes Earth's atmosphere fundamentally different from, say, the atmosphere of Mars or Venus. Not just because water exists here, though that matters enormously, but because water does something almost magical from a thermodynamic perspective. It changes phase. It goes from vapor to liquid to solid and back again, and every time it changes phase, it either absorbs or releases a tremendous amount of energy. When liquid water evaporates, when it turns from liquid to gas, it absorbs energy from its surroundings. You feel this every time you step out of a swimming pool on a breezy day and feel cold. The water on your skin is evaporating, and it's pulling heat from your body to do it. That energy doesn't disappear. It gets stored in the water vapor molecule as what physicists call latent heat, hidden heat. The energy is there, locked up, invisible, carried along wherever the wind takes that water vapor molecule. And then, when that water vapor condenses back into liquid, when it forms a cloud droplet, it releases all that stored energy back into the surrounding air as heat. Think about what that means for the atmosphere. Every cloud you see is a heat engine. Every time water vapor condenses into droplets, it warms the air around it, and warm air rises, which can cause more condensation, which releases more heat, which causes more rising. It's a feedback loop, and it's the engine that drives the most powerful weather phenomena on Earth. Thunderstorms, hurricanes, the towering cumulonimbus clouds that can reach from near the surface all the way to the tropopause, 50,000 feet up or more. The amount of energy involved is staggering. A single average thunderstorm releases energy equivalent to roughly a 20-kiloton nuclear weapon, about the size of the bomb dropped on Nagasaki. a mature hurricane releases that much energy every few seconds. And all of it comes from water changing phase, from vapor condensing into droplets and releasing its latent heat. This is why meteorologists sometimes call water vapor the fuel of the atmosphere. It's the energy source that powers storms, and it's also the mechanism by which heat gets transported from the surface, where the sun warms the ground and the oceans, up into the higher atmosphere where it can be radiated away into space. And understanding this, understanding the role of water vapor, latent heat, and phase changes, was one of the great intellectual achievements of 19th century physics. The person who arguably did the most to put it all together was Rudolf Clausius, the German physicist who helped formalize the laws of thermodynamics in the 1850s. But the atmospheric application of these ideas, the realization that latent heat release was the primary driver of convective storms, came from a whole community of researchers working through the late 1800s and into the early 1900s. And the person who pulled all of these threads together, the large-scale circulation, the thermodynamics of water, the physics of rotating fluids, into something that could actually be used to predict the weather, was a Norwegian physicist named Wilhelm Bjerknes, working in the early 20th century. And his story is one of the most remarkable stories in the history of science, because Bjerknes didn't just advance our understanding of the atmosphere. He essentially invented the idea that weather forecasting could be a rational physics-based enterprise rather than a folk art or a guessing game. Wilhelm Bjerknes was born in 1862 in Christiania. That's what Oslo was called back then, and he grew up steeped in physics. His father, Carl Anton Bjerknes, was a mathematician and physicist at the university who spent decades studying hydrodynamic analogies to electromagnetic forces. The father was brilliant, but also somewhat tragic. He worked obsessively on ideas that never quite gained the recognition he felt they deserved. And young Wilhelm grew up watching this, absorbing both the intellectual intensity and the painful awareness that great work can go unnoticed if you don't communicate it well. That shaped him. Wilhelm became determined not just to do important science, but to make sure it reached the world. He studied in Christiania and then went to Germany, where he worked with Heinrich Hertz. Yes, the Hertz of radio waves, the person whose experiments confirmed Maxwell's electromagnetic theory. Bjerknes was Hertz's assistant in Bonn in the early 1890s, and working with Hertz taught him something crucial about how physics operates at its best. You take fundamental mathematical principles, you derive predictions from them, and then you test those predictions against reality. That loop, theory, prediction, observation, refinement, became the core of everything Bjerknes would later do with the atmosphere. After Hertz died tragically young in 1894, Bjerknes returned to Scandinavia and gradually turned his attention from electrodynamics to fluid dynamics, and from there to the atmosphere. And here's where his big idea crystallized. By the late 1890s, Bjerknes had become convinced of something that sounds obvious now, but was genuinely revolutionary at the time. The atmosphere is a physical system governed by known physical laws, and therefore, in principle, if you know the current state of the atmosphere with sufficient precision, the temperature, pressure, humidity, and wind velocity at every point, you should be able to calculate its future state using the equations of fluid dynamics and thermodynamics. Weather prediction, in other words, isn't magic. It's math. It's just really, really hard math. In 1904, Bjerknes published what's sometimes called his Weather Prediction Manifesto, a paper laying out this vision explicitly. He identified the core equations you'd need: the equations of motion for a fluid on a rotating sphere, the thermodynamic energy equation, the continuity equation for mass conservation, and the equation of state-relating pressure, temperature, and density. 7 equations, 7 unknowns. In principle, solvable. In practice, of course, the equations are non-linear, partial differential equations that can't be solved analytically for anything resembling real atmospheric conditions. You'd need to solve them numerically on a grid covering the entire atmosphere at thousands of points and then step them forward in time. In 1904, this was pure fantasy. There were no computers. The calculations would have taken armies of human mathematicians working around the clock, and even then, they'd have been too slow. The weather would arrive before the forecast was finished. But Bjerknes understood that even if the full numerical approach wasn't yet feasible, the framework mattered. If you accepted that weather was governed by physics, then every improvement in observation, every refinement of the equations, every advance in computational power would bring you closer to useful forecasts. He was laying down a research program that would take decades to fulfill, and he knew it. So while waiting for the mathematics to become tractable, Bjerknes took a different approach. He moved to Bergen, Norway in 1917 during the First World War, and there he established what became known as the Bergen School of Meteorology. And this is where things get really interesting, because the Bergen School didn't just advance atmospheric science. It gave us the conceptual vocabulary we still use today when we talk about weather. Norway during World War I was neutral but economically squeezed, and the government needed better weather forecasts for agriculture and fishing, practical life and death stuff. Bjerknes was given funding to set up a dense network of weather observation stations across western Norway, and he staffed his research group with young, talented scientists, including his own son, Jacob Bjerknes, who was barely 20 years old. And what this team discovered, by analyzing their detailed observations, was something beautiful and profound about how weather actually organizes itself in the mid-latitudes. They found that weather systems aren't just random swirls of air. They're structured around boundaries, sharp, relatively narrow zones where large masses of air with different temperatures and humidity levels collide. The Bergen School called these boundaries fronts, borrowing the military terminology of the war that was raging across Europe. A cold front is where a mass of cold air is advancing and pushing under warmer air ahead of it. A warm front is where warm air is advancing and riding up over cooler air. The language was deliberately martial, and it stuck. We still use it every single day in weather forecasts, more than a century later. Here's the thing about fronts that made them so powerful as a concept. Before the Bergen School, meteorologists tended to think about weather in terms of pressure systems, highs and lows, and they'd draw isobars on maps and try to infer what was happening. The Bergen School showed that the really important action was happening along these frontal boundaries, where the temperature contrasts were sharpest. That's where the clouds formed, where the rain fell, where the winds shifted, and the fronts weren't static. They moved, they interacted, they had life cycles. Jacob Bjerknes, Wilhelm's son, published a landmark paper in 1919. He was just 21, describing the life cycle of what he called an extratropical cyclone. This is the classic mid-latitude storm system that brings most of the significant weather to places like Europe, the northern United States, and Japan. And what Jacob showed was that these storms are born along the polar front, the boundary between the cold polar air mass and the warmer subtropical air mass. Think of it like this. You have these two enormous bodies of air sitting next to each other, one cold and dense, one warm and lighter, and there's this boundary between them. Now, that boundary is unstable. Small perturbations, a little kink in the flow, can grow. The warm air starts pushing poleward in one spot while the cold air pushes equatorward in another, and this creates a wave along the front. The wave deepens. Pressure drops at the center. The system starts to rotate, counterclockwise in the northern hemisphere, because of that Coriolis effect we talked about earlier. A warm front extends ahead of the storm center, with warm air gently rising over the retreating cold air, producing widespread clouds and steady rain. A cold front trails behind, with cold air aggressively undercutting the warm air, producing a narrower but more intense band of heavy rain and sometimes thunderstorms. And then, and this is the really elegant part, the cold front moves faster than the warm front because the cold air is denser and pushes more forcefully. So eventually, the cold front catches up to the warm front. When that happens, the warm air gets lifted entirely off the surface, squeezed upward between the two cold air masses. This is called occlusion, and it marks the beginning of the end for the storm. The energy source, that temperature contrast at the surface, gets cut off, and the cyclone gradually weakens and dissipates. This whole life cycle, from initial perturbation to mature storm to occlusion and decay, typically plays out over 3 to 5 days. And it explained so much. It explained why mid-latitude weather tends to come in waves, why you get a sequence of warm then cold, why the clouds change character as a storm approaches. First, the high, thin cirrus clouds far ahead of the warm front, then thickening layers, then steady rain, then a brief warm spell, then the dramatic cold front passage with its squalls and clearing skies. If you've ever watched the weather change over the course of a couple of days, you've watched Jacob Bjerknes's cyclone model play out in real time. Now, the Bergen School's frontal model was brilliant, but it was also, in a sense, a workaround. It was a way of understanding weather without actually solving those impossible equations that Wilhelm Bjerknes had identified back in 1904. The frontal approach was qualitative and conceptual. It told you what to look for, how to interpret observations, how to draw a weather map. But it wasn't the full numerical prediction that Wilhelm had dreamed of. That dream was still waiting for someone brave enough, or perhaps foolish enough, to actually try the calculation. And someone did try. His name was Louis Fry Richardson, and his story is one of the most poignant in all of science. Richardson was an English mathematician, physicist, and Quaker pacifist who served as an ambulance driver in France during World War I. And between shifts carrying wounded soldiers, in the chaos and horror of the Western Front, he sat down and attempted to calculate the weather using Bjerknes's equations, by hand, on paper, in a war zone. Richardson divided a section of the atmosphere over Central Europe into a grid, a coarse grid by necessity, with cells roughly 200 kilometers on a side and 5 vertical layers. He took observed weather data from a single day, May 20th, 1910, and tried to compute what the atmospheric conditions should be 6 hours later by numerically stepping the equations forward. The calculation was enormous. It took him months of work, filling stacks of paper with arithmetic. And when he finally got his answer, it was spectacularly wrong. His predicted pressure change for a single point in Central Europe was about 145 millibars in 6 hours. The actual change was essentially 0. His forecast was off by a factor of, well, infinity, more or less. It was a failure, a magnificent, instructive, visionary failure. Richardson published his work anyway in 1922, in a book called Weather Prediction by Numerical Process, and in it he was remarkably honest about what had gone wrong. Part of the problem was the initial data. The observations weren't precise enough or closely spaced enough. Part of it was the grid resolution, too coarse to capture what was actually happening, and part of it was a subtle mathematical issue involving the way pressure and wind fields needed to be balanced at the start of the calculation. If your initial conditions contain even tiny inconsistencies, the equations amplify them catastrophically. This is a problem that would later be called initialization, and solving it would take decades. But here's what makes Richardson's story so moving. Despite the failure, he could see the future clearly. In his book, he imagined what he called a forecast factory. A vast hall, like a theater, with a giant map of the globe painted on the interior walls. 64,000 human computers would sit in tiered galleries, each one responsible for calculating the equations for their small patch of atmosphere, passing results to their neighbors, all coordinated by a conductor in the center with a beam of light, like an orchestra conductor, keeping everyone in sync. It was a vision of massively parallel computation, decades before electronic computers existed. Richardson estimated that 64,000 people working in concert might just barely keep up with the weather, producing forecasts at the same speed the actual weather unfolded. He wrote this with a kind of wistful humor, knowing it was impractical, but also knowing that someday, somehow, the calculation would become possible. And he was right. It just took a world war, a revolution in electronics, and a mathematician named John von Neumann to make it happen. Von Neumann, who was arguably the most brilliant polymath of the 20th century, recognized in the mid-1940s that weather prediction was the perfect problem for the new electronic computers being developed at places like the Institute for Advanced Study in Princeton. The atmosphere was governed by known equations. The problem was purely computational. You just needed enough speed and memory to grind through the arithmetic. And the payoff was enormous, both scientifically and, not incidentally, militarily. In 1950, a team led by Jules Charny, working on von Neumann's computer at Princeton, produced the first successful numerical weather forecast. They used a simplified version of the atmospheric equations, a single-layer model that captured the large-scale flow patterns, and they computed a 24-hour forecast for North America. It took about 24 hours of computer time to produce, so they were just barely keeping pace with the weather itself, exactly as Richardson had imagined. But the forecast was recognizably correct. The large-scale pressure patterns, the movement of the major troughs and ridges, it worked. Not perfectly, not in fine detail, but it worked. And that changed everything. Within a few years, operational numerical weather prediction centers were being established around the world. The calculations got faster as computers improved. The models got more sophisticated, more vertical layers, finer horizontal grids, better representations of moisture, radiation, surface interactions. By the 1960s, numerical forecasts were routinely outperforming human forecasters for large-scale weather patterns. By the 1980s, they were becoming genuinely skillful several days out. Today, a 5-day weather forecast is about as accurate as a 1-day forecast was in 1980. That's an extraordinary improvement, and it's built directly on the foundation that Wilhelm Bjerknes laid down in 1904 and that Richardson tried to implement by hand in a muddy field in France. But there was a catch, a deep, fundamental catch that no amount of computing power could fully overcome. And it was discovered, almost by accident, by a quiet, unassuming meteorologist at MIT in the early 1960s. His name was Edward Lorenz, and what he found would reshape not just meteorology, but our entire understanding of what it means for a system to be predictable. Because that's the word, right? Predictable. We use it all the time without really thinking about what it means. We say the weather is unpredictable, and we mean it loosely. It's hard to forecast. It surprises us. We packed the wrong jacket. But Lorenz stumbled into something much more precise and much more unsettling than that. He discovered that certain kinds of systems, and the atmosphere is one of them, have a built-in mathematical limit to how far into the future you can ever predict them, no matter how good your instruments are, no matter how powerful your computers become. Not because we're not smart enough, because the physics itself won't allow it. Here's how it happened. It was the winter of 1961, and Lorenz was running a simple weather simulation on a Royal McBee computer, a desk-sized machine that was modest even by the standards of the day. He'd built a stripped-down model of atmospheric convection, just 12 equations, nothing like the full complexity of a real weather model, but enough to produce interesting, realistic-looking patterns, swirling flows, shifting pressure systems, the kind of output that looked like weather even if it wasn't real weather. And one day, he wanted to re-examine a particular sequence. So instead of running the whole simulation from the beginning, he picked a point partway through, typed in the numbers from an earlier printout, and let it run forward from there. A shortcut. Save some time. He went down the hall to get a cup of coffee. When he came back, the new run had diverged completely from the original. Not just a little bit. Totally. The weather patterns that had developed in the second run looked nothing like what the first run had produced from the same point forward. At first, he assumed the computer had malfunctioned, but then he looked more carefully at the numbers he'd typed in, and he realized what had happened. The computer's internal memory stored numbers to 6 decimal places, something like 0.506127, but the printout, to save space, only showed 3 decimal places, 0.506. So, when he'd restarted the run, he'd rounded the initial conditions by less than 1 part in 1,000, a difference so tiny it should have been completely insignificant, and yet that minuscule difference had amplified, doubling and redoubling with each time step, until after a simulated couple of months, the two runs bore no resemblance to each other whatsoever. Think about what that means. It means that in this system, and by extension, in the real atmosphere, the tiniest imaginable difference in starting conditions leads to completely different outcomes. Not eventually, not after geological ages, but within a practical forecasting time frame. The errors don't just grow, they grow exponentially. A whisper becomes a shout, becomes a roar. Lorenz later captured this idea with a famous question he posed as the title of a 1972 talk. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? He wasn't being poetic, he was being precise. The answer, mathematically, is that you can't rule it out. In a system with this kind of sensitivity, perturbations at any scale, even the scale of a butterfly's wing beat displacing a few cubic centimeters of air, can cascade upward through the non-linear dynamics until they alter the large-scale flow. This property came to be called sensitive dependence on initial conditions, and the broader framework it belongs to became known as chaos theory. Now, the word chaos is a little misleading because it sounds like randomness, like the system is just doing whatever it wants with no rules. That's not what's going on at all. The equations governing Lorenz's model were completely deterministic. No randomness anywhere. Given perfectly precise initial conditions, the future would be perfectly determined. The problem is that perfectly precise is impossible in practice. You can never measure the atmosphere's state with infinite accuracy. There will always be some error, some unmeasured gust, some temperature reading that's off by 1/100th of a degree. And in a chaotic system, that irreducible uncertainty grows until it swallows your forecast whole. Lorenz worked out that for the real atmosphere, this imposes a theoretical predictability limit of roughly 2 weeks. Beyond about 14 days, the amplification of initial errors becomes so large that a forecast is essentially no better than climatological averages, no better than just saying, well, it's usually about this temperature in July. You can push that limit around a little bit, depending on the situation. Some atmospheric patterns are more predictable than others, some seasons, some regions. But the fundamental ceiling is there, and it's not going away. No computer that will ever be built, no satellite network that will ever be launched, no sensor array that will ever be deployed can push useful deterministic weather forecasts much beyond that 2-week horizon. It's not a technology problem. It's a mathematics problem. And here's the thing. This was a genuinely revolutionary insight, and not just for meteorology. Before Lorenz, the prevailing assumption in physics was essentially Laplacian determinism. If you know the initial state of a system precisely enough and you know the laws governing it, you can predict its future indefinitely. Pierre-Simon Laplace had articulated this view back in 1814, imagining a vast intelligence that could see all the forces and positions of every particle in the universe and thereby compute the entire future. Quantum mechanics had already put a crack in that dream at the subatomic level. But for large-scale classical systems, weather, fluid flow, planetary motion, most scientists still assumed that better measurements and bigger computers would yield better predictions without limit. Lorenz showed that this assumption was wrong. Deterministic systems could be fundamentally unpredictable in practice, not because the laws were incomplete, but because the laws themselves generated exponential sensitivity to conditions you could never fully know. The impact rippled far beyond weather forecasting. Chaos theory turned out to be relevant to fluid turbulence, population ecology, cardiac arrhythmias, the orbits of asteroids, stock market, dynamics, the dripping of a faucet, an astonishing range of systems that share this same mathematical fingerprint of sensitive dependence. But the atmosphere was the original example, the system where it was first discovered, and in some ways it remains the most vivid one. Because we all live inside the atmosphere. We all experience its unpredictability every single day. But, and this is important, Lorenz's discovery did not mean that weather forecasting was hopeless. Quite the opposite. It meant that there was a well-defined challenge. Push the boundary of useful prediction as close to that 2-week limit as possible, and develop entirely new approaches for saying useful things about the atmosphere beyond it. And meteorologists rose to that challenge in some remarkably clever ways. One of the most important innovations came in the 1990s with the development of ensemble forecasting. The idea is beautifully simple once you hear it. If tiny differences in initial conditions lead to wildly different forecasts, then instead of running your model once with your single best estimate of the current atmosphere, you run it dozens of times, sometimes 50 or more, each time with slightly different starting conditions that are all equally consistent with the observations you actually have. Each run gives you a different forecast. If most of the runs agree, say 48 out of 50 show a major storm hitting the coast on Thursday, then you can be fairly confident. If the runs scatter all over the place, that itself is valuable information. It tells you the atmosphere is in a state where small uncertainties matter a lot and your confidence should be low. Instead of giving you a single prediction that's either right or wrong, Ensemble forecasting gives you a probability distribution. There's a 70% chance of rain, not because the forecaster is hedging, but because literally 70% of the plausible futures contain rain. This was a profound shift in how we think about prediction. It moved meteorology from determinism to probabilism, and it made forecasts far more useful. A farmer deciding whether to harvest, an airline planning fuel loads, an emergency manager deciding whether to evacuate, they all need to know not just what might happen, but how confident we should be that it will happen. Ensemble forecasting gives them that, and it comes directly from taking Lorenz's insight seriously rather than trying to pretend it doesn't exist. And then there's the question of what happens beyond that 2-week wall. You can't predict the specific weather on March 15th 6 months from now, but can you say anything useful about whether next winter will be warmer or colder than average? Whether the coming monsoon season will bring more or less rain than normal? This is the domain of climate prediction, and it operates on completely different principles than weather forecasting. It doesn't try to predict the specific sequence of storms and sunny days. Instead, it predicts the statistics, the averages, the extremes, the probabilities. And those statistics are governed by slower-moving factors that are much more predictable. Ocean temperatures, for instance. The El Niño Southern Oscillation, that great seesaw of warm and cold water in the tropical Pacific, operates on timescales of 2 to 7 years, and its state profoundly influences weather patterns across the globe. When a strong El Niño develops, you can say with genuine skill that the coming winter will likely be wetter in the southern United States and drier in Australia. You can't say it'll rain in Los Angeles on January 12th, but you can say the odds of a wet January are elevated. That's a different kind of prediction, and it's not limited by Lorenz's butterfly. This distinction between predicting weather and predicting climate is one of the most important and most frequently misunderstood ideas in all of atmospheric science. People sometimes say, if you can't predict the weather next week, how can you predict the climate in 50 years? And it sounds like a reasonable objection, but it misses the point entirely. It's like saying, if you can't predict which specific card will come up next in a shuffled deck, how can you predict that a casino will make money this year? The casino doesn't need to predict individual cards. It needs to know the odds, and the odds are set by the rules of the game. Climate prediction works the same way. The rules of the game, the energy balance, the greenhouse effect, the ocean circulation patterns, determine the statistical envelope within which weather fluctuates. Change the rules, and you change the envelope, even though the individual fluctuations remain chaotic and unpredictable. And this brings us to something that connects all the threads we've been following: the energy balance of the atmosphere itself, the question of how much energy comes in from the sun, how much gets trapped, how much escapes back to space, and what happens when you shift that balance. Because it turns out that the atmosphere has been keeping a kind of ledger, an energy budget, for as long as it's existed, and humans have been altering the entries in that ledger for about 2 centuries now, in ways that the atmosphere is responding to, with exactly the kind of physics we've been talking about all along: radiation, convection, phase changes of water, the whole interconnected system. The person who first understood that this ledger even existed, who first calculated that certain gases in the atmosphere could trap heat and change the planet's temperature, was a Swedish chemist working in Stockholm in the 1890s. His name was Svante Arrhenius, and he's one of those figures who shows up in chemistry textbooks for entirely different reasons. He won the Nobel Prize in 1903 for his work on electrolytic dissociation, the way salts break apart into ions in solution. That's what he's famous for. But on the side, almost as a hobby, he tackled a question that nobody else was really paying serious attention to at the time. He wanted to know why ice ages happened. What could possibly make the entire planet cool down enough to cover Scandinavia in kilometers of ice, and then warm back up again? And in pursuing that question, he ended up doing something remarkable. He sat down and calculated, by hand, how changes in the concentration of carbon dioxide in the atmosphere would affect the Earth's surface temperature. Now, Arrhenius wasn't starting from nothing. The basic physics of heat-trapping gases had been worked out decades earlier. In the 1820s, Joseph Fourier, the same Fourier famous for his work on heat conduction and the mathematical technique we call Fourier analysis, had pointed out something that should have been obvious but wasn't. He noted that the Earth's atmosphere acts like a kind of blanket. Sunlight passes through the atmosphere and warms the surface, but the surface doesn't just absorb that energy and sit there getting hotter and hotter. It radiates energy back outward as infrared radiation, heat radiation, the same kind of warmth you feel radiating off a hot stove, even from across the room. Fourier realized that if the atmosphere were perfectly transparent to this outgoing infrared radiation, the Earth's surface would be much colder than it actually is. Something in the atmosphere was catching some of that outgoing heat and sending part of it back down. The atmosphere was warm, not just because the sun heated it directly, but because it was trapping energy that was trying to leave. Then, in the 1850s and 60s, an Irish physicist named John Tyndall did the actual laboratory work to figure out which gases were doing the trapping. And here's what's fascinating. It's not the main gases. Nitrogen and oxygen together make up about 99% of the atmosphere, and they're essentially transparent to infrared radiation. They don't absorb it. They let it pass right through. The gases that do the trapping are the minor ones: water vapor, carbon dioxide, methane, and a few others. Tyndall set up experiments where he passed infrared radiation through tubes filled with different gases and measured how much got absorbed. Water vapor turned out to be the most powerful absorber. Carbon dioxide was next, and Tyndall immediately grasped the significance. He wrote that removing water vapor and carbon dioxide from the atmosphere would change the climate dramatically, that England's fields would be buried beneath ice, as he put it. So Arrhenius had Fourier's insight and Tyndall's measurements to work with. What he added was the calculation. He wanted to know, quantitatively, if you doubled the amount of carbon dioxide in the atmosphere, how much warmer would the planet get? And to do this, he had to work through the problem zone by zone, across the Earth's surface, accounting for latitude, for the angle of incoming sunlight, for the amount of water vapor at different temperatures, for the way the atmosphere absorbs and re-emits radiation at different altitudes. It was a monumental calculation. He did it by hand, with pencil and paper and tables of data, working through thousands of individual computations. It took him over a year. His wife left him during the process, though to be fair, their marriage had other problems, and he later described the work as tedious beyond belief. But when he finished, he arrived at a number. Doubling carbon dioxide would raise global average temperatures by about 5 to 6 degrees Celsius. Here's the thing that should give you chills lying there in the dark. Modern climate models, running on supercomputers with millions of lines of code and satellite data and ocean measurements that Arrhenius couldn't have dreamed of, estimate the climate sensitivity to a doubling of carbon dioxide at somewhere between 2.5 and 4.5 degrees Celsius, with a best estimate around 3 degrees. Arrhenius was high, but he was in the right ballpark in 1896 with pencil and paper. That's extraordinary. Now, Arrhenius wasn't alarmed by his finding. He was Swedish. He thought a warmer world might be rather pleasant, longer growing seasons, more comfortable winters. He even speculated that burning coal might eventually warm the climate enough to prevent future ice ages, and he seemed to regard this as a good thing. He had no way of knowing how fast industrial carbon dioxide emissions would grow over the coming century, and he assumed the process would take thousands of years. He was wrong about the timeline, but he was right about the physics. And the physics is worth understanding, because the greenhouse effect is one of those things that almost everyone has heard of, but relatively few people can actually explain correctly. So let's take a minute with it. Think about the Earth floating in space, receiving energy from the sun. The sun's surface is about 5,500 degrees Celsius, and at that temperature, most of the energy it emits is in the visible light range, the wavelengths your eyes can detect. This sunlight travels across space, hits the top of the atmosphere, and about 30% of it gets reflected straight back to space by clouds, ice, and bright surfaces. That's the albedo, the reflectivity. The remaining 70% gets absorbed, mostly by the surface, land, and ocean, which warms up. Now, any object that has a temperature radiates energy. The Earth's surface, at an average temperature of roughly 15 degrees Celsius, radiates energy too, but at much longer wavelengths than the sun does. This is infrared radiation. You can't see it, but it's there, streaming upward from every square meter of ground and ocean. And here's where the greenhouse gases come in. Carbon dioxide, water vapor, methane. Their molecular structures happen to vibrate at frequencies that match certain wavelengths of infrared radiation. When an infrared photon at the right wavelength hits one of these molecules, the molecule absorbs it, vibrates more energetically, and then re-emits infrared radiation in a random direction. Some goes up, some goes sideways, and critically, some goes back down toward the surface. This is the greenhouse effect. The atmosphere is not like a greenhouse in the literal sense. A real greenhouse works mainly by preventing convection, by physically trapping warm air under glass. But the name has stuck. What's actually happening is selective absorption and re-emission of infrared radiation by trace gases. The net effect is that the surface receives energy from two sources, the sun from above and the atmosphere's own infrared radiation from above. This makes the surface warmer than it would be if the atmosphere were transparent to infrared. How much warmer? About 33 degrees Celsius. Without the greenhouse effect, Earth's average surface temperature would be about -18 Celsius, well below freezing everywhere. The oceans would be frozen. Life as we know it would be impossible. So the greenhouse effect isn't a problem in itself. It's the reason the planet is habitable. The question is, what happens when you enhance it? And this is where the story connects back to everything we've been tracing. The convection cells, the water cycle, the jet streams, all of it. Because when you add more carbon dioxide to the atmosphere, you're not just warming the surface a little bit, you're perturbing the entire system. Warmer air holds more water vapor. Remember the Clausius-Clapeyron relationship? About 7% more water vapor for every degree Celsius of warming. And water vapor is itself a greenhouse gas, the most powerful one. So adding carbon dioxide warms things up, which puts more water vapor into the air, which traps more heat, which warms things up more, which puts more water vapor into the air. This is a positive feedback loop. It roughly doubles the warming you'd get from carbon dioxide alone. But it doesn't stop there. Warmer temperatures melt ice and snow, which are bright and reflective, replace white ice with dark ocean water, and the surface absorbs more sunlight instead of reflecting it. More warming. Another positive feedback. This is why the Arctic is warming 2 to 3 times faster than the global average. That ice albedo feedback is most powerful where there's ice to melt. And remember what we talked about earlier, how Arctic amplification affects the jet stream, weakens the temperature gradient between the poles and the equator, makes the Rossby waves wobble more, and can lock weather patterns in place for days or weeks. That's not a separate story. That's the same story. It's all connected. The carbon dioxide changes the radiation balance, which changes the temperature distribution, which changes the pressure patterns, which changes the winds, which changes the weather you experience on any given Tuesday afternoon. There are negative feedbacks too, processes that push back against warming. Warmer temperatures increase evaporation, which can mean more clouds, and clouds reflect sunlight back to space. That's a cooling effect. But clouds also trap infrared radiation. That's a warming effect. Whether clouds net out as a positive or negative feedback depends on the type of cloud, its altitude, its thickness, and where it forms. Low, thick clouds tend to cool. High, thin clouds tend to warm. The cloud feedback question has been one of the most stubborn problems in climate science for decades. It's probably the single biggest source of uncertainty in those climate sensitivity estimates. And this is where the modern machinery of atmospheric science, the numerical models, the satellite observations, the global networks of sensors, all come together on a question that Arrhenius first posed with pencil and paper in a Stockholm apartment. The models that climate scientists use today are direct descendants of the ones Charney's team ran on ENIAC in 1950, and of Richardson's dream before that. They solve the same fundamental equations, the primitive equations of fluid dynamics on a rotating sphere, coupled now to radiation transfer equations, ocean circulation models, ice sheet models, land surface models, atmospheric chemistry models. A modern Earth system model might have 1 million lines of code and run on thousands of processors simultaneously, dividing the atmosphere into grid cells, maybe 50 to 100 kilometers across horizontally and a kilometer or so vertically, stepping forward in time in increments of minutes. But here's what's really interesting about these models, in the context of what Lorenz taught us about chaos. Remember, weather is chaotic. Sensitive dependence on initial conditions means you can't predict specific weather events more than about 2 weeks out. Climate models run for centuries of simulated time. They're not trying to predict the weather on March 15, 2070. They're trying to predict the statistics, the averages, the extremes, the probability distributions, and those statistics are determined by the boundary conditions, the energy balance, the rules of the game. Change the concentration of greenhouse gases, and you change the rules, and the statistics shift accordingly, even though individual weather events remain unpredictable. The evidence that this shift is happening is not just in the models. It's in the measurements. It's in thermometers and tide gauges and ice cores and tree rings and coral records and satellite data spanning decades now. The atmospheric concentration of carbon dioxide has risen from about 280 parts per million before the Industrial Revolution to over 420 parts per million today, a 50% increase. Global average surface temperature has risen by roughly 1.2 degrees Celsius since the late 1800s. Sea levels have risen by about 20 centimeters. Arctic sea ice extent in summer has declined by about 40% since satellite measurements began in 1979. These aren't model predictions. These are observations. The models predicted these trends before they were fully observed. which is one of the strongest forms of scientific validation there is. And what makes all of this so compelling, from an atmospheric science perspective, is that none of it requires any new physics. Every piece of the puzzle, radiation absorption by greenhouse gases, convective heat transport, the Coriolis effect, latent heat release in storms, the fluid dynamics of jet streams and Rossby waves, every single piece was worked out by the people we've been talking about all along. Fourier, Tyndall, Arrhenius, Bjerknes, Richardson, Rossby, Charney, Lorentz. The atmosphere is doing exactly what the physics says it should do when you change its composition. There's something almost elegant about that, even as the implications are sobering. The same equations that let us forecast tomorrow's weather, the same thermodynamics that explain why hurricanes spin and why monsoons arrive on schedule, the same radiation physics that keeps the planet habitable in the first place. All of it points in the same direction when you add more carbon dioxide. And that brings us to something I find genuinely beautiful about the atmosphere. Something that ties together everything we've explored tonight, from Torricelli's mercury tube all the way to satellite-era climate monitoring. It's the idea that this thin shell of gas wrapped around a rocky planet is not just a passive backdrop to life on Earth, but an active, dynamic, evolving system. One that responds to every input, remembers every perturbation, and connects every living thing on this planet through the simple act of circulating heat and moisture from one place to another. That's what the atmosphere really is. It's a machine, yes, in the sense that it obeys physical laws and can be modeled with equations. But it's also a kind of living membrane, constantly adjusting, constantly in conversation with the oceans below it and the sunlight above it and the gases being breathed out by every organism and every smokestack and every volcanic vent on the surface. And you know what strikes me most about that? It's how personal it is. Right now, wherever you are, you're lying in this ocean of air, and every breath you take is part of the system. The oxygen entering your lungs was produced by photosynthesis, maybe by a tree in your neighborhood, maybe by phytoplankton in the Southern Ocean weeks ago, carried to you by the same large-scale circulation patterns that Hadley and Farrell and Rossby spent their careers trying to understand. And the carbon dioxide you're exhaling right now will mix into the atmosphere, get caught up in those same winds, and within a year or two, it'll be distributed across the entire globe. A molecule of CO2 you breathe out tonight could end up above the Sahara, or over Antarctica, or absorbed by a kelp forest off the coast of Tasmania. The atmosphere connects you to everywhere. It always has. And here's the thing. That connection is what makes the modern challenge so different from anything humanity has faced before. Because for most of our history, the atmosphere was so vast, so incomprehensibly large compared to human activity, that we couldn't meaningfully change it even if we tried. When Torricelli was measuring air pressure in the 1640s, the global population was maybe 500 million people, most of them burning wood for heat and using animals for transport. The idea that humans could alter the composition of the entire atmosphere would have seemed absurd. Even Arrhenius, when he did his carbon dioxide calculations in 1896, treated it as an interesting theoretical exercise. He actually thought a warmer world might be pleasant. He was Swedish, after all, and long winters were no joke. He estimated it would take thousands of years for industrial emissions to double atmospheric CO2. He was wrong about the timeline, but not about the physics. What changed was scale. The 20th century brought an explosion in fossil fuel use that nobody in the 19th century could have anticipated. Global coal consumption doubled, then doubled again. Then oil took off. Then natural gas. The numbers are staggering. humanity now emits roughly 40 billion metric tons of carbon dioxide per year. 40 billion tons every year. And the atmosphere, vast as it is, has a finite capacity to absorb that without changing. It's like, imagine you have a bathtub with the drain slightly open. Water trickles in from the faucet, and for a long time the drain keeps up. The water level stays roughly stable. Natural carbon sinks, the oceans, forests, soils. They're the drain. They absorb about half of what we emit, but we've been turning the faucet up year after year, and the drain can't keep pace, so the water level rises. That's what's happening with atmospheric CO2. It was about 280 parts per million before industrialization. It passed 400 in 2015. As of the early 2020s, it's above 420. That's higher than it's been in at least 800,000 years, based on ice core records from Antarctica. Probably higher than it's been in several million years. And what I want you to appreciate, and this is really the culmination of everything we've talked about tonight, is that understanding what that means requires every single layer of atmospheric science we've walked through together. You need Tyndall's radiation experiments to know why CO2 absorbs infrared. You need Clausius-Clapeyron to understand why a warmer atmosphere holds more water vapor, amplifying the warming. You need the three-cell circulation model to understand how heat gets redistributed from equator to poles. You need Rossby wave dynamics to understand why a warming Arctic can send polar vortex air plunging into Texas. You need Bjerknes's frontal theory to understand how storm tracks shift. You need Richardson and Charney's numerical methods to actually simulate all of this on a computer. And you need Lorentz's chaos to understand why we can project climate trends decades out, even though we can't forecast the weather past 2 weeks. Every piece matters. Nothing we talked about was idle curiosity. It all builds to this. And the people working on this right now, the atmospheric scientists, the climate modelers, the oceanographers, the glaciologists, they're standing on the shoulders of every person we've mentioned tonight. When a researcher at NOAA runs a coupled Earth system model on a supercomputer, that model's dynamical core is solving the same primitive equations that Charney used in 1950, just on a finer grid with more physics included. When a meteorologist at the European Center for Medium-Range Weather Forecasts issues a 10-day ensemble forecast, they're using Lorentz's insight about sensitive dependence to quantify uncertainty. When a graduate student studies how clouds respond to warming, that unresolved question we talked about, they're extending Tyndall's work on radiation, trying to pin down whether low clouds will thin out and let more sunlight in or thicken and reflect more back to space. The intellectual lineage is direct and unbroken. And I think there's something deeply reassuring about that, even when the news about climate change feels overwhelming. Because it means we understand this system. Not perfectly. The cloud feedback question alone tells you there are still genuine uncertainties, but the fundamental physics is solid. It's been tested and retested for over a century and a half. We're not guessing. We're not speculating. We're applying well-established physical principles to a well-observed system, and the observations keep confirming the theory. That's science working exactly the way it's supposed to. Now I should say, and this matters, understanding the physics doesn't automatically tell you what to do about it. That's a question for policy, economics, ethics, politics. Atmospheric science can tell you what will happen if CO2 reaches 500 parts per million, or 600, or 800. It can tell you how much warming to expect, how much sea level rise, how storm patterns will shift, which regions will get drier and which will get wetter. But it can't tell you how to weigh those costs against the costs of transitioning energy systems, or how to distribute the burden fairly between nations that industrialized early and nations that didn't. Those are human questions, not physics questions. What the atmosphere gives us is clarity about the physical stakes. And that clarity is a gift, even when the message is uncomfortable. But let's step back from the heavy stuff for a moment, because I want to end where we started, in a way. Think about the air around you right now. Just the air in your room. It's pressing on you with a force of about 10 tons per square meter. Torricelli's ocean of air, remember? You don't feel it because you grew up in it, because the pressure inside your body matches the pressure outside, but it's there, and that air is a mixture. 78% nitrogen, 21% oxygen, a little less than 1% argon, and then those trace gases, the ones that punch far above their weight. 420 parts per million of CO2, about 1.9 parts per million of methane, tiny amounts of nitrous oxide and ozone, and water vapor, varying from almost nothing over a cold desert to maybe 4% in a tropical rainforest. That's it. That's the whole recipe. And from that recipe, from those few ingredients stirred by solar heating and spun by a rotating planet, you get everything. You get sunsets, you get thunderstorms, you get the gentle breeze coming through your window on a summer night. You get the jet stream steering weather systems across continents. You get the monsoons that feed billions of people. You get snowflakes, each one a tiny masterpiece of crystal physics. You get the blue sky, which, by the way, we never even talked about, and it's such a lovely piece of physics. It's Rayleigh scattering. Sunlight hits nitrogen and oxygen molecules, and shorter wavelengths, blue light, scatter more than longer wavelengths. So when you look up, you see scattered blue light coming from every direction. At sunset, the light travels through so much more atmosphere that most of the blue has scattered away, and what's left is red and orange. That's it. That's the whole explanation. Lord Rayleigh worked it out in the 1870s. Simple, beautiful, and true every single day. And you get the greenhouse effect, not as a problem, but as a fundamental feature. Without any greenhouse gases at all, Earth's average surface temperature would be about minus 18 degrees Celsius. That's 0 Fahrenheit. The whole planet, a frozen ball. It's the greenhouse effect, the natural one, the one that's been operating for billions of years, that warms us to a livable average of about 15 degrees Celsius. Life as we know it exists because of trace gases trapping infrared radiation. The problem isn't the greenhouse effect. The problem is that we're enhancing it faster than ecosystems and human societies can adapt. But the mechanism itself is what makes Earth habitable. Tyndall knew that. He wrote about it explicitly. He understood that without those trace gases, life on Earth would be impossible. So here you are, lying in this ocean of air, breathing this ancient mixture, kept warm by the physics of molecular vibration, sheltered from space by a thin blue line that astronauts always say is the most striking thing they see from orbit. How impossibly thin the atmosphere looks against the blackness of space. It's maybe 100 kilometers to the edge of what we'd call atmosphere, and most of the mass is in the lowest 10 or 12 kilometers, the troposphere, where all the weather happens. That's it. A film of gas thinner, proportionally, than the skin on an apple. And within that film, all of the physics we've explored tonight plays out, continuously, everywhere, all at once. The winds are blowing right now. Somewhere over the Pacific, a Rossby wave is meandering, steering a low-pressure system toward the coast of British Columbia. Somewhere over the Indian Ocean, warm, moist air is rising in a towering cumulonimbus, releasing latent heat that drives the Hadley cell. Somewhere over the Sahara, dry air is descending, clear and cloudless, completing the circuit. The jet stream is threading its way around the northern hemisphere, wobbling and splitting and reforming, carrying weather with it. Storms are forming, storms are dying, fronts are sweeping across prairies and oceans and mountain ranges, all of it governed by the same physics, all of it connected. And we figured it out. That's the part that gets me. Humans, fragile, distractible, short-lived humans, looked up at the sky and, over the course of a few centuries, figured out how it works. Not completely, not perfectly, but deeply, rigorously, beautifully. From Aristotle's first clumsy attempts to Torricelli's Mercury column, to Hadley's circulation theory, to Coriolis's mathematics, to Tyndall's laboratory experiments, to Bjerknes's vision of physics-based forecasting, to Richardson's impossible dream of numerical prediction, to Charney, making it real, to Lorenz, discovering that the dream had a ceiling, and then finding ways to work within that ceiling anyway. It's one of the great intellectual achievements of our species, and it's ongoing. Every day, people are refining the models, launching new satellites, deploying ocean buoys, releasing weather balloons, studying ice cores, analyzing tree rings, running simulations, asking questions, pushing the boundaries of what we understand. The atmosphere doesn't care about any of this, of course. It just does what physics tells it to do. It absorbs radiation and re-emits it. It convects. It circulates. It rains. It clears. It has been doing this for 4.5 billion years, and it will keep doing it long after we're gone. But for now, tonight, you're part of it. You're breathing it. You're warmed by it. And maybe, as you drift off, you can hold on to that thought, that the air around you is not empty space, not nothing, but a vast, intricate, interconnected system that took some of the most brilliant minds in history to begin to understand. And they did it the way all great understanding happens. One question at a time, one experiment at a time, one insight building on the last, across generations and centuries, with patience and curiosity, and stubbornness and wonder. So let the air hold you. Let it press gently against you with its 10 tons per square meter. Let it carry warmth to you and carry your breath away into the wider world. The atmosphere is doing what it's always done, circulating, balancing, responding, connecting. And now you know, at least a little, how it works. That's enough for tonight. That's more than enough. Let it go. Let it all settle. And sleep